Okay, so we stated this theorem last time and we want to prove it now. And we went through some few lemmas, nearly 5 or 6 lemmas. The theorem just says that if A is any n cross n, 2n cross n, 2n matrix, then we have a symplectic dilation for that. And the order of the dilation is going to be of order, the 2n plus 2m is going to be that number. 4C2, it's a big number. Okay. So we have proved that any direct sum of matrices where each entry has a symplectic dilation and then we proved convex linear combination of combination of matrices which has symplectic dilation and any strictly positive matrix, any symmetric matrix, all these things have symplectic dilation, which we have proved. And we also proved that any skew symmetric matrix in the form D minus D transpose, that also has a symplectic dilation. We have proved all that. So we want to use that. So okay, so we have this A. We can write A as half A plus A transpose, of course, minus half into A minus A transpose. Okay. In this is a symmetric matrix, of course. So let A1 equal to this half A plus A transpose, and we have proved that this has symplectic dilation of order 8n. That's what we proved. Okay, 8n, we have proved that. So now we have to, so this is one thing we keep aside. So A equal to A1 plus A2 plus A3. Let's write it like this, where A1 is already there. And A2 is something. So A2 plus A3 is going to be that, the remaining one. There is a minus sign. That's okay. I mean, if some A is symplectically dilated, then can be symplectically dilated, then minus A also can be symplectically dilated. Okay, so A2 plus A3 we have to write. So let A2 is this. So maybe minus A2 I will write. That is okay. A2 is this. It is just the A11 minus A11 transpose, half of this. And then I minus AII transpose. This is just the diagonal one. ANN. Yeah, these are all 2 cross 2 matrix. A11 minus A11, that is 2 cross 2 matrix. ANN transpose. Then zeros everywhere else. Okay. And we know that any 2 cross 2 matrix or not, we don't know. Once you submit the assignment, we know that any 2 cross 2 matrix can be symplectically dilated to 4 or order 4. And then the direct sum can be dilated. So this A1 can be dilated. So this A1 can be dilated to n. And A2, this can be dilated. Can be dilated to order. So it should be 4 and n, 4n again. Okay, there are n of them. So each entry can be dilated, so the direct sum can be dilated. So this is it. So only we have to handle this A3. Now we have to handle this A3 and then the sum also. To handle the sum, notice that, I mean, if you multiply by any number k, this thing, each entry will be multiplied by k, and that is just a 2 cross 2 matrix. Okay, and that again can be dilated, and the direct sum can be dilated. So k times A2, any k times A2 can be dilated. I mean, A1 can be dilated, and any k times A1 can also be dilated. Okay. I mean, it is just the same. Any symmetric matrix can be dilated. So multiply by a number, it can be dilated. Similarly, A2, you can multiply, each entry will be dilated. Okay. So similarly, A3, we want to consider. Now the A3, we write it like this, Bij, okay, where I is greater than or equal to 1, but I is strictly less than j. I is not equal to j. J is less than or equal to n. Where each Bij, I mean, what is the remaining one? We have already got, so this A equal to A1 plus A2 plus A3. A1 is a symmetric matrix, A plus A transpose by 2. So A2 plus A3 is that. And there we have taken the diagonal entry. Only the off diagonal entry we have to worry. Okay. So each of the off diagonal entry, I mean, this is because we want to apply whatever we know, whatever the lemma we know. So, okay. So Bij is going to be, Bij has block diagonal, something like this. 0 everywhere else. And then there is a ijth block. This is a, I mean, this is a 2n cross 2n matrix. 2n matrix. Okay. With ijth block, we have this. I mean, the ijth block is here, which is Aij minus Aji. Okay. I mean, Aij, which is, yeah, Aij, I mean, that transpose. So transpose half of this. Okay. That is how it will look like. And here it will be minus of that, which is 1 by 2 Aji minus Aij. So it's 0 everywhere else. Okay. I mean, 0 everywhere else. The ijth entry is that, jth entry is this, and 0 everywhere else also. Okay. This is here also it's 0, here also it's 0, 0, 0. Okay. It's like this. Ijth entry is this. This is the ijth entry, and this is the jith entry. Okay. This is what Bij is. Then this A3 is just the summation of those things. I mean, there should be a minus here. Okay. Right? Minus is there. No. It is just plus. I'm sorry. There is no minus. It is just the plus of those things. Of A plus A transpose, A minus A transpose. The A transpose will cancel. Sorry. There's no minus. Okay. So Bij is like this. Now we first verify that each Bij can be dilated. What is this Bij? Bij has ijth entry like this, jth entry like this. And it's a skew symmetric matrix with the D, something like this. D looks like, I mean, it is a D. This is the D matrix. We include 0 and everything. It is just D minus D transpose is here, right? It is of this form. This is equal to Dij. I mean, you call it Dij, the matrix, minus Dij transpose 0, 0, where you include the zeros, everything. Okay. Sigma ij, I mean, Bij is the matrix with the ijth entry like this. Dij is the matrix with which is just the n cross n matrix. Dij is n cross n matrix. Okay. N cross n matrix with ijth entry that. And this is just the transpose of that. Okay. Entry that half Aij minus Aij Ji transpose. Okay. Okay. Now we know that this can be dilated to 4n, right? We have proved that. Okay. This can be dilated to 4n. Hence, k times that also. I mean, in particular, this I mean, now this can, since k times Bij can also be symplectic for any k, can also, I mean, that's also a skew symmetric matrix of this form, can also be dilated to order 4n. Okay. Now, what do you have? We have this A is equal to A1 plus A2 plus summation Bij greater than or equal to 1 less than j less than or equal to n. Less than or equal to n, right? It's not equal to n. Yeah, it's a block diagram, so n cross n matrix. So how many of them? This can be dilated to 4n. This can be dilated to 4n, and each Bij can be dilated to 4n, and there are NC2 terms there. Okay, the number of terms is NC2 terms, right? And you have to choose 2 out of n. And because, I mean, you can't permute it because I is strictly less than j. So this is just in NC2 terms. So this sum, you can write it like this: 1 by k, 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 k. where k equal to that number of terms, total number of terms. Then it will be a convex linear combination. K times that also can be dilated. Then 1 by k, if you take it, then now you can take the sum. Okay. You are taking those matrices whose constant times that also can be dilated. Now we have the theorem. Okay, that theorem says any constant multiple also cannot be dilated, where k is equal to the number of terms, which is just nc2 plus nc2 plus 2, nc2 plus 2. But then, I mean, this is a1 is dilated to of order 8. I mean 8n, right? So this can be dilated to symplectic matrix of order 8n is so I mean, so this is basically 4n into nc2 plus 3. Okay. Because the first one is 8n, second one is 4n, then this is k times 4n, each one is 4n, so we got the theorem. That's all. So we proved the theorem. So every 2n cross 2n matrix can be dilated to something, some big 2n plus 2m matrix. You want the proof?
What was the order?
The order is k times that. I mean, if you have k terms, each one can be dilated to some n. Okay, some 2m, say let's say 2m or 2k, whatever. So if each bij can be dilated to 2n plus 2m, where m is the number occurring there, then k times that, k is the number of terms.
So this has to be like k will come outside and 1 over k will be.
K will come outside, right? So right. So the k is this 4 nc2 plus nc2 is the k here. And then there are 3 terms there. So nc2 plus 3, 4 times 4n. Yeah. Each one can be dilated to order 4n. I mean, first one is 8n. So you have to put a 2 there. Next one 4n. Each one is 4n. So you have to multiply by k. Okay. Okay, so this follows from all the lemmas we have proved. Okay, so we move on to the new topic if this is finished. Okay. So here we want to consider what are called channels, Gaussian channels. Gaussian channels. So that is what we want to do in this class. So before that, so since we have done some quantum probability in the last semester, so let me say a few things. Why we do this? In probability theory, if you have a probability space, omega, it's just a probability. I mean, this is just a measurable space, not probability space. And you have a collection of measures on that, low probability measures. You have a collection of probability measures on omega script f. Then you have another measurable space. Okay. Then you can talk about maps from here to here. The map will be, but I mean, it's a function from omega to omega prime. But you mention the script f because it should be measurable with respect to that. T inverse of something should land up here. It should be measurable. Okay. So it will actually give a function from f prime to f. Okay. If there is a function from omega to omega prime, then using the inverse, it will give a function from f prime to f. Okay. So that can be extended to a function to L infinity to L infinity corresponding. Okay. I mean, whenever this is always the case. If you have even if you have C of x, for example, if you have a map from one compact metric space to another compact space is compact T2, right? So one x1 to x2, then C of x2 to C of x1, you will get a corresponding. The morphism will come the other way. Okay. So you will get a map from the algebra. The map is the other way. Okay. So we would like. So this is a nice map in one. So this will actually take measures from here to measure. Okay. If you have a transformation, then you can define the measure using the inverse, right? If you have a measure mu, if you have a transformation, then you can T inverse of E. You can define a measure. Okay, mu will go to mu inverse. So if you have a transformation between the probability spaces, I mean, whatever the measurable spaces, then you have a mapping from the. Then we have the. Then we have the map between the measures like that. So this is something very nice. Once you have some transformation, you will have something like that. We want to, so this is what is called an operation, and what are the kind of operation. And there are not too many of them. I mean, you can with some even you can determine all of them. That's okay. That's measure theory. That's probably. So we want to here we want to talk about something. We have an algebra. A is an algebra, some nice algebra, and finite dimension. You don't have to worry. It is just an algebra is enough. But if it is, but we are dealing with infinite dimension. Okay, so if it is an infinite dimension, you have to talk about what is called a phenomenal algebra, C-star algebra. Depending upon that, you have to say. But we will be dealing with B of H. Okay, so we don't worry what is the algebra. But just I'm calling it as an algebra. It has to be a phenomenal algebra. Better it's C-star algebra or something. It's nice algebra. Okay, then you want to talk about the generalization of probability measure on an algebra in the non-commutative is a state. I mean, for us, it is supposed to be a state, but since we have B of H, okay, since V of H, the states are given by states, we want that to be continuous with respect to weak star topology. So we take we get states from the pre-dual, which is trace class operator. That is how we get the trace class operator, right?
States are distributions, right?
States are
will be distribution.
Distributions means the states
like
are
a probability distribution corresponds to a state, right? Or
no probability measure. Measure is distribution in finite dimension. There is no difference.
Yeah.
Finite dimension, there is no thing. It's a probability measure will correspond to state basically. State is basically a probability measure. When you say distribution, it's fine. I mean, distribution. I mean, what distribution?
Yeah.
How do you want to whether have a density or something? I mean, if you there is nothing like that. I mean, density means then you have to have another measure to talk about the density and all that. Right?
Yeah. I mean, aren't like trace functions kind of like measures?
No, state, the generalization of a probability measure is a state. Okay. See, you have a probability measure. You replace that measure with the integration with respect to that. That gives the linear functional. That linear functional is a state on L infinity. So you instead of talking about measure and other thing, you can talk about state on L infinity, which is equivalent to. Okay. So the non-commutative setting, we talk about generally state. If it's as if, we want to deal with probability measure, so we are having the, I mean, it has to evaluate identity as to 1. Okay. Phi of 1 should be 1. Okay. Okay. Now we have two algebras, A, B are algebras. Okay. Nice algebras, whatever you want to consider. Okay. Then what are the states? States are nothing but this is all those phi from A to C. Okay. Linear functional bounded. I mean, actually, phi of 1 equal to 1 will make, I mean, and it's positive linear functional. That is phi of x star x is greater than or equal to 0. Okay, for all x in A. X star x is all positive elements. Okay, every part, or you can say positive element should be greater than or equal to 0. So this will automatically make it continuous. It will norm will be equal to 1 also. This is a theorem. When we did this representation theory, we did a continuous version of it, but I mean, commutative version of it. But this is true. The same proof will work for a general thing. We actually did something. You used something like that when you prove this representation theorem.
You'll have to take like, you'll have to look at the positive things and check if it is unbounded, then maybe there'll be a sequence which keeps going like 1 over 2 and x star x.
Not sure. Not like that. Not like that. We consider the unit interval and did something that it maps into unit interval. Here also it will the same thing will work.
Unit.
Something like that. It will map that into. I mean, if it is bounded by some norm, then the range will also be. I mean, it's something to do with that. Okay. Okay. So this is the collection of state. Okay, all those linear functional which are positive linear functional such that phi of 1 equal to 1. They are automatically bounded. Okay, so this is contained in A star. Okay, A star. Now we want to consider map T from A plus 1 star to B plus 1 star. Okay, it should take state to state. That is the only. What? One is phi of one is one state. Plus is for positivity. One is for phi of one. It's unital. Okay. Phi of one is one. Okay. We want probability measure. That's why I put a one there. Okay. So, okay. Further, we want one more condition. We want it to be, this is a convex set, right? You can take convex linear combination of state, that will be again a state. You can, I mean, linear functional, you can take linear combination. If you take convex linear combination, it will be a state again. So it has to take that, it has to be an affine map. We better, I mean, that's a property we will require. Okay. I mean, it will satisfy in the measure case, and I mean, we will better have an affine map. T is an affine map. When we have a convex set, we can't talk about linearity. We have to, I mean, because if you multiply by something, it will go out of the set. So we want to talk about affine map. So we want to consider this kind of affine map from here. Okay, that is T of lambda phi are states. Okay, lambda phi 1 plus 1 minus lambda phi 2 should be equal to lambda times phi 1, lambda same T of phi 1, which is a state, of course, and 1 minus lambda T of phi 2. And it actually follows that this, this collection of state will generate the whole everything. Okay. It is actually true that any state can be written as difference of two positive linear functional. And from that, it will follow that any linear functional can be written as difference of positive linear functions. Okay. It is actually true. I'm not going to prove it. Okay. So it follows that any linear functional can be written as linear combination of four states. No, not what I said is not true. You have to, I mean, any symmetry, I mean, you have to some sort of self-adjointness. Phi of x star should be phi of x bar. Those linear functional can be written as difference of positive linear functional, and any linear functional can be written as linear combination of four state. Okay, four state. So because of that, this T will be always given by a linear map. This can be extended to a linear map. Okay, it will actually follow. Okay. So T is actually it will follow. I'm not proving it. This is just to sketch you how we have to deal with completely positive maps. Why are we dealing with that? Okay. So it will follow that T extends or T is just a restriction of linear T from A star to B star. Okay. But then if you have something like that, then this is actually, so this is A and B are dual of that. Okay. This will be a dual map of something between B to A. See, if we have dual map from two Banach spaces X to Y, then there is a dual map will be defined from Y star to X star using this. T star of phi at X should be phi of Tx. I should call this as T star. Okay, let me call this T star. Okay, then there exists T star. Okay, T tilde star. Okay, so then any T star, there will be a T on the pre-dual. Okay, so the T star is just the dual of that. And it is actually true that if that T is positive, that is it. I mean, so there is a positivity in the A star, right? There is a collection which are called positive linear functional. Okay, so we would like the T star to be positive. T star take positive linear functional to positive numbers. That's the requirement, because you have to take. So, actually, this T star is given by T star is positive. Sorry, it's not just any linear functional. T star is positive linear functional. T star phi is greater than or equal to 0 for all phi greater than or equal to 0. Where phi is a positive linear functional. Phi is positive linear functional if phi takes positive elements of A to B, positive numbers in C. Okay, positive real numbers, right? Okay. So it will actually follow, if you just think about it, T star is positive if and only if T is positive. What is T? T is a map from T is from B to A. T is from B to A. Okay. And T star is from A star to B star. Okay. So this is positive is equivalent to this is positive. I mean, T takes positive elements of B to positive elements of A. Okay. T star will take positive elements of A star to positive element, positive linear functional to positive B star. Okay. This is actually true that if these things are true. This is not very difficult, but we can work it out. Okay. But in quantum mechanics, in quantum theory, it is not enough to have this positivity. The reason is, if you have to deal with joint system, okay, and then you have to act this phi at this operate, you have to operate only on one system. Joint system is given by tensor product. Okay. B of H1 is one of them, then you can tensor with another Hilbert space, and you can get a giant system. But you want to operate it on one system. Still, you want it to be positive. It will not continue to be positive when you consider the giant system and operate it on one of them. If you have T, then you have to talk about T tensor 1 on the bigger system, amplified one. T tensor 1 need not be positive if T is positive. Because of this entangled things. Okay. Because tensor product is not just tensor product. Okay, we shouldn't get confused with the tensor product deals with linear combination of that. See, if we have a T is a map from A to B, okay, then if you can tensor A with Mn, okay, you can take the joint system, okay, and you can have B to MNC. Okay. Now you can write T tensor 1 from here, where any elementary things, A tensor some A will go to T of A tensor A. But these are only generating elements. You have to take linear combination of such things. But there is this entanglement and another thing. Not everything can be written in this form, right? Because of that, it need not be, I mean, things which are positive need not be positive when you consider the giant system. Okay. So you want things to be positive in the giant system also. This is a requirement in the non-quantum setup. Okay. That is what is called completely positive. For all n, you want it to be positive. Okay. But in if your algebra A is commutative, then it will automatically follow that it will be completely positive. Positivity will imply completely positive. Okay. So only in the quantum setup, non-commutative setup, it's not true. So we would one more thing we should remember is we can deal with completely positive. So again, completely positive map, T is completely positive map, positive if and only if T star is completely positive. Because it is just you are tensoring some Mn there, and here also you are tensoring some Mn there. Okay, and A, I mean, this is true, no? A tensor Mn. I mean, I haven't proved it. This is actually you can identify with again Mn star, which is Mn itself. This is easy to see. So because of this, if something is completely positive, then I mean that is also dual. I mean, T tensor 1, it's a dual map, T star tensor 1. Okay. So if T is positive, if and only if T star is positive. So T is completely positive is equal to T star is completely positive. So we can deal with any one of this map, T or T star. You can deal with states, which takes state to state, or you can deal with this map. Okay. So what we are dealing with, what we are dealing with depends on the situation. Here in this paper, so this is just for clarity, I'm just saying. In this paper, so we have this H is equal to L2 of Rn. For what we are going to work with. You don't need all this algebra and all this theory. Okay. For us, our A will be B of H, right? B will also we take to be B of H. There is no difference. And what is our A star? A star is B1H, in fact. Right? And that is how we are dealing with trace class operators. Okay. So it is actually the linear function which matter, but we are actually dealing with B1H itself. Okay. So the dual map will be between not A star, A dual star. Sorry. A star is this. There is something I forgot. It's actually one will, if you have a C star algebra, you will deal with dual state. But we would require one more condition for phenomenal algebras. When we deal with phenomenal, B of H is phenomenal algebra, whatever it is. Okay. We prove phenomenal algebra, all those there. No? Yeah, it's a phenomenal algebra. So for a phenomenal algebra, we would like to deal with what are called normal linear function, normal state. Normal means it is continuous with respect to weak star topology. Okay. Weak star topology means the topology given by the pre-dual. So, okay, A star star, this A star, whatever, we have, what I wrote is not correct. B1H star is B of H. Okay. So we want it to be weak star continuous. Okay. So that is why we are dealing with B1H. The dual of B of H is very big. Okay. It's not separable. B1H is separable. Okay. So that is some big thing. Okay. So we are dealing with B1H, which are normal state, normal linear function. Normal means weak star continuous, just in word. Okay. Normal means weak star continuous. Okay. So that is why we are dealing with A star. Okay. So what do you want to do? So now a channel is just a continuous, is a completely positive map. Positive map T from P of H to B of H. P of H, which preserves the trace on I mean, it's completely positive is enough. The dual will I think it preserves the trace, I think. Hmm?
It should preserve taste.
Yeah. No, I mean, I'm just wondering whether we consider the dual map or the is map. Is a positive, I mean, channel is a completely positive, trace preserving linear map on the algebra B of H of bounded operators on Hilbert space. Of course, the trace is infinity, that's also infinity, that's what it means. But of course, the trace is not defined, well defined for that, only for positive operator, trace is well defined. Okay. I mean, otherwise, infinity minus infinity is not defined. Okay. So when you restrict to trace class operator, it preserves the trace. Okay. Or if you have, see, if you have a map from B of H to B of H, that will induce a map between the, it will induce a map on the dual, of course. It will indeed induce a map between the, I mean, we don't need to consider, let us consider between B1H to B1H, okay, for the time being. Only on the, let's be B1H, B1H, trace preserving. Okay. Okay. Then T star can be defined between B of H to B of H. Okay. Yeah. Sorry. I mean, I am just defining a T between B1H to B1H, trace class operator, which preserves the trace. Okay. Then if you want, you can have a T star, which is between B of H to B of H. Okay. You can deal with that. Let us have this. Anyway, we want to consider all trace preserving map between B1H to B1H. That's what we want to consider. It need not be defined on B of H. Okay. Okay. So examples of channels. Any add U for U be any unitary, then any automorphism of B of H, then add U is a channel, of course. It preserves the trace. If you take the trace, U star will cancel. Trace of rho is equal to trace of U rho U star. You can bring that U there, and the tracial property will ensure that it preserves the trace. Okay. And it is a completely positive map because in this T rho equal to I rho. So the one tens are If you amplify it, it is just 1 tensor add u. That's all. 1 tensor add u is 1 tensor u. Add of 1 tensor u, right? 1 tensor add u on any b of, any b of h tensor mn is just add of, here 1 is the identity automorphism. Here 1 is identity automorphism. Here the 1 is identity operator, okay? Please, 1. This is the identity operator tensor u, right? See, the map, this extension is completely positivity. This is the definition. This is the actual definition. If T from some A to B be the map, then T tensor 1 acting on A tensor, 1 tensor A or A tensor Mn or Mn tensor A, doesn't matter. Mn to B tensor Mn. This is nothing but Mn of A. All those matrices with entries coming from A. This is the tensor product, okay? To Mn of B. That is what the tensor product is. In B of H, it is of course clear. If you have B of H tensor MNC, this is just B of H tensor Cn, right? So which are just matrices with entries coming from B of H. At least here it is clear, right? You don't even, I haven't defined what is the tensor product of A tensor M and all that. You have to define it for general algebra. Let us take A to be B of H. And when you take A to be B of H, then B of H tensor Mn is nothing but B of H tensor Cn, right? Right? Mn is just a B of Cn. Okay. B of H1 tensor B of H2 is B of H1 tensor H2. Okay. So take that as a definition of tensor product of algebras. Okay. So this is Mn A to Mn B. So what will happen is if we have a entries with this T tensor 1 of this Aij will be T of Aij. That's all. If you look at, the one T tensor 1 is actually defined on elementary tensor and it is extended. Okay. And this extension is precisely this. Okay. And this has to be completely positive. Completely positive map will be automatically bounded. Okay. This, in fact, what is called completely bounded. That is, if you take T, see, completely bounded means if T is bounded, that's a bounded definition. T tensor 1 is bounded for all Mn. This is 1 n. Okay. This is 1 n. For all n, if it is bounded, that's what is called completely bounded. Because positive matrix, which are unital, which are T tensor 1 is bounded for all n. No, it's okay. You don't have to worry about it. Okay, now it's just a statement. Okay, it's just a positivity will imply boundedness if it is. If phi of 1 is something, so phi of 1 has to take some value number, so it will be automatically bounded. Okay? So that will be the norm. Okay, so this has to be, so positivity means this has to be positive. So why was I talking about all these things? Now, if you take add u, which is just an automorphism, add u of rho, okay, is going to be, so 1 tensor add u is going to be add of 1 tensor u. Correct? At least an elementary tensor you can verify, and that generates everything. From that it follows. Okay. I'm just saying 1 tensor add u is just add of one tensor. This one is the identity automorphism on Mn. Identity 1. That tensor add u is just add of 1 tensor u, right? Okay. So because of that, this any add map is positive map, right? Any add map is positive. Add of x star x is going to be u x star. You can put a u star in the middle, x, and this is just sorry, U star U in the middle. Okay. Now this is something star something. So this is positive. Add map is a positive map. Okay, it takes positive element to positive element. So one tensor U, I mean, so the add U is positive. I mean, add U is completely positive. That's clear, right? Okay. Next, we consider some tensor. Okay, example 2. Okay, here we are taking different algebras. Okay. Define T from B of H to B of H, B of H tensor H1, H prime. Okay. Let rho prime is a state. I mean, we are actually going to define it for a state, but we can state on H prime, B of H on H prime. Then the map T of rho is going to be rho tensor rho prime. This is clearly completely positive because one tensor T, okay, acting on, suppose some rho is a state on, I mean, rho is in MNC. I mean, just state on MNC means it's just a trace one operator, okay, MNC, some rho naught. Then rho naught tensor rho is going to be rho naught tensor rho. I mean, because it's going to be identity. So it's rho naught tensor rho prime only, right? So which is again positivity preserving that, right? Okay, if rho naught is positive, rho is positive, that's also positive. So you can tensor it, that is positivity preserving mapping, and that's completely positive. Okay, so this is also completely positive. Okay, the next one I want to recall is the trace map. Okay, so trace 2, trace 1 or trace 1, okay, is a map from B of H1 tensor H2 to B of H1. Okay, so which is just x going to trace 1 of x, trace 2. I mean, we are tracing out the second coordinate. Okay, trace 2 of x. You just, I mean, we have done the calculation. No, this is an operator in B of H1. And this operator for xi eta in H1. This xi trace x trace to x eta. So this will tell you what the operator is. That's going to be summation over k xi tensor ek x acting on eta tensor ek. Okay, where ek is an orthonormal basis for H2. Okay, this is how that is defined. The trace is defined. Okay. Okay. So from this, it's clear if we have xi, if x is positive, if x is positive, x is a positive operator, then trace to x xi is equal to summation over k xi tensor ek x of eta tensor that's also xi. Xi tensor ek. Okay, and this is greater than or equal to 0, right? So it's positivity preserving map. It's positive. So this implies the trace map, whatever the trace to map is a positive map. Positive map. It's a map between two algebras, B of H1 tensor H2 to B of H1. Okay. In fact, one nice thing you can see that this trace 2 is a dual of tensoring map. What is trace 2 map? Trace 2 is uniquely defined. Trace 2 of x is unique element satisfying this condition. Satisfying unique element, maybe we call it some t is already there, maybe xy A, unique element A in B of H1, okay, such that trace, this is the trace, our usual trace, okay, trace of trace to X, Y is equal to trace of X, Y tensor 1. Correct? We have defined it like that. This just say that trace 2 is nothing but is equal to this map. I mean, trace 2 is a map. See, we define a map T from B of H1 to B of H1 tensor H2. Okay. Okay. Which is just T. Maybe the T is already there. So I call it A. A going to A tensor 1. Okay. Then T star is equal to trace 2. Trace 2. That's what this says, right? This says. Right? Right? How does it say? That is because you acted as linear functional. I mean, the linear functional on phrase class operator is given by B of H using the trace, right? So that is a linear functional acting on X is acting as linear functional on that, and you are acting it on Y tensor 1. That gives a linear functional on this. You have to think about it. It's not very clear, easy. Yeah, say it again. I mean, what I'm saying is, see, the point is, if you have a map, something from T from A to B, then T star is a map from B to A star. Okay, B star to A star. This B star are linear functional there, such that T star of phi is a linear functional on B, right? Of some B is equal to phi of TB. TB will land up in B, right? That is how this T star is defined. Okay. If you see how the linear functional is defined on trace class operator and all that, it will follow that the trace 2 is nothing but the dual of this tensoring map, amplification map, whatever. So you can easily see that this amplification map is certainly positive map. Trace 2 is just the dual of that. Okay, this is positive. That's a different proof, but we have directly proved anyway. Yeah, using this representation, we have directly proved trace 2 is a positive linear function. It is completely positive linear functional is again, if you want to talk about so 1n tensor trace 2. Okay, this is a map from Mn tensor B of H1 tensor H2 to Mn tensor B of H1, right? What was completely positive? T is positive, you know, you take positive element at all. One tensor T is positive from Mn tensor A, that's all. You amplify it, one tensor T, that has to be positive.
So T is completely positive.
One tensor T, that's the definition. So that's what we are doing. Trace 2 is positive, you have seen, using that expansion. Okay. Now I am saying one tensor trace 2 is also positive to prove completely positiveness. That is because one tensor trace 2 is something like this, which is also actually a partial trace only. You are just tracing. So this is actually one tensor T. This is actually actually a trace 2 map. I mean, trace 2 maybe this is a map from B of Cn tensor H1 tensor H2 to B of Cn tensor H1, right? I mean, this is a different trace 2. I mean, it's just the, okay, which is again a partial trace only. This one tensor trace 2 is nothing but it's again a partial trace only, but on a different, right? Okay, so this is positive. This is completely positive. Okay, so we know that when you amplify, that is completely positive. If you take a rho tensor rho naught is completely positive. Then you can conjugate by a unitary add map, which is an auto, that's a completely positive. Trace 2 is completely positive. We combine all these things to get what is called symplectic channels. Okay, so that is what we do. So this is the definition. This is not a definition, okay, construction or definition, whatever. Okay. We take our H to be L2 of Rn, the Fock space. Okay. Fock space. Okay. And a rho naught be a state, rho naught be a, I mean, it's a trace class operator, whatever. Okay. It's just a state. Here trace means trace positive trace class operator with trace equal to 1. Okay. Rho naught is a state on L2 of Rm. Okay. Rm. Okay. And L is a symplectic map. L is in SP. Did I use capital? SP 2n plus 2n. Okay. L is a symplectic map in 2n plus 2m. Okay. Then a symplectic channel given by this rho naught and this L is rho naught is a state on Rm, L2 of Rm. Okay. So a T of any rho is equal to, first you take rho tensor rho naught. Now this becomes a state on L2 Rn tensor L2 Rm. Okay. Now you use the gamma of L. Okay. Gamma of L star, L inverse, whatever you want, or even transpose. Okay. Now you take the trace to. Okay. This is a state on L2 of Rm. This T is called a symplectic channel. Again, composition of completely positive map is completely positive map. Of course, because composition of positive map is positive map, right? It takes positive element to positive element. If you apply again another map of positive map, it will take to positive element, right? Okay. The composition of positive map is positive. Composition of completely positive map is completely positive. So here we are composing 3 completely positive map. Rho going to rho tensor rho naught is completely positive. Conjugated with gamma L is unitary. Okay. L is symplectic, gamma L is second quantization, it's a unitary. So conjugating with gamma L, add gamma L is completely positive, then the partial trace is completely positive, the whole thing is completely positive. This is what is called symplectic channel given by rho naught and L. Okay. Given a rho naught and L, we can define some collection of completely positive maps like this. This is what is called symplectic channel. Okay. So I want to see, I mean, we can actually compute the characteristic function. So assume now that rho naught is Gaussian. Okay. Then you want to say that this is so a channel is called Gaussian channel if we take Gaussian map to Gaussian state to Gaussian state. Okay. Gaussian if P rho is Gaussian for a channel for rho Gaussian. Okay. Rho is Gaussian, then T rho is also Gaussian. That's what's called a Gaussian channel. Okay. Definition. Okay. So yeah. Now we can replace this C. We have already seen, I mean, we have some M. Okay. On that M, we have a state rho naught. Okay. Now we know that any state, Gaussian state can be purified. Pure state on L2 Rm. See, rho naught can be purified. I mean, it's you have a pure state on a big purified to L2 of Rn, tensor L2 of Rn, the same thing. Using that, whatever, the L and M. Rho naught will be given by L and M. Okay. Then you can use that 45-degree rotation. Huh? Yeah.
And then trace it.
Exactly. Take the partial trace and you will get that. You rotate it by 45 degree and then get it. So because of that, so because it can be purified, you can take that M instead of Rm, you can take it be R2M. Okay. You can assume that rho naught is a pure state. Okay. And we assume that rho naught has mean 0. Also, rho naught, maybe here itself, we assume that rho naught is a state with mean, I mean, it's a, with a let us assume it's a Gaussian state, okay? Gaussian state with mean 0. Okay? So, any mean 0 Gaussian states are all given by, so without loss of generality, we can assume by taking a bigger m, replacing m by 2m, we can assume that rho naught is equal to gamma of L, this pure state. That is how any pure state will look like, right? Gamma. We have calculated all the pure state. If you apply the W operator, further, if you apply the W operator, you will get all Gaussian state. But then the mean will be something else. Mean will not be 0. Okay? So you get all Gaussian state, it means 0, looks like this. Now you have a L, you replace, I mean, maybe gamma M, you can put M. L is already there. Okay. Now instead of that L, if you put L, you take this M, you call it L prime or whatever. Okay. Now replacing L with L, one tensor L prime. Okay. So you can assume that rho naught is actually that vacuum state, E0, E0. Okay. So you just have a symplectic operator on a bigger space. So any Gaussian channel, any symplectic Gaussian channel. So I mean, this is the statement I want to make. Any symplectic Gaussian channel, there is no rho anymore. Okay, that's what I'm saying. There will be a gamma L, and that gamma L will be absorbed into that L. Okay. You can take L into 1 plus L prime or something. Okay. So not 1 plus L, 1 direct sum, right? It should be direct sum. Sorry. Tensor comes in the top, not in the ground. So any symplectic Gaussian channel, symplectic Gaussian channel is given by L in SP to n plus maybe 2k if you want. Okay. Such that T of rho should be rho tensor, you take this tensor. Okay. 0. Then you take the gamma L star. Then you take the trace 2 of this. Okay, this is how it is. So you can actually calculate, right? You know, if you know the rho, characteristic function of rho, you know the characteristic function of rho tensor E0, E0. Then you know by conjugation what happens to the characteristic function, you know. Then what happens trace 2? You will only take the first entry. So you know the characteristic function, how it does that. Okay. And it is clear that this is a Gaussian channel. From that, it is clear that it's a Gaussian channel. If you have rho is a Gaussian state, rho tensor that vacuum vector is also a Gaussian state. If you conjugate by gamma L, it's still a Gaussian state. If you trace it out, it's still a Gaussian state. So this is a Gaussian channel. Symplectic Gaussian channel. I wrote it Gaussian channel, but it follows.
If rho is a Gaussian state.
Yeah, if rho is a Gaussian state, this is a Gaussian. This is a Gaussian channel. So we can actually calculate it. Shall I do it? You can, I mean, using this L, we can calculate that, right?
Yeah.
I will leave it to you. Okay, it is there. Okay, so yeah, I stop here. Or I will do it in the, I mean, okay, so we can just do that. If L is equal to, so what is the T rho hat? You want to calculate T rho hat. If rho is equal to some rho G, which G means Gaussian, with mean some L, you can call it LM or L plus L minus IM. I mean, it's actually there is a minus because you want to take imaginary part of inner product. No. The notation is if you use real one LM, if you want to use the complex number, it is L plus I minus IM.
Yeah, but we have been doing with the real R2N, right?
Yeah, R2N it is LM. So
Yeah.
you have to, I mean, there will be a minus. Something minus something you will get. It depends on what we have used. It doesn't matter. We know how to write it. Okay, LM, and there is a S here. Okay, S is a 2n cross 2n matrix. If rho is that, then T hat rho we want to calculate. You know, this E0, this E0, this hat. This is with mean 0, and this is just rho G 0 with half of I. Yeah, I mean, yeah, whatever that K, I2K. Half of the identity. So this is its covariance, right? Okay. So this tensor, I mean, and it has mean 0. The mean is going to get added. So this hat, rho tensor, this E0. This hat is going to be just the product, and product means within the exponential, you just add up. So which is just going to be rho G. You just add LM plus 0, 0. I mean, LM sitting in the big one. Okay, LM direct sum 0, 0. Okay, because you want to write it in the bigger one, right? And here it is going to be S direct sum of I2K, right? This is how it will look like. Now we want to trace it out. Okay, now we want to now we want to apply the gamma L. So you will get L inverse. So if M equal to L inverse, okay, you take M to get L inverse. I mean, here L inverse will act on that, right? So L inverse will act on this LM, but then you are going to take only the, I mean, it will not bring anything in the first n terms only. You have to take it, right? Because you are going to take the trace out. I mean, if you want to consider this part, the whatever inside that will be you have to apply the L inverse to the mean, and L inverse, whatever the covariance matrix times L, right? That's what you L inverse transpose, whatever the covariance matrix times L, right? That's what you will get. Okay. So if you have if M looks like this, M11, M12, M21, M22. Okay. But then when you are going to trace out, you are going to take the first n entries. Okay. So then this T row hat is going to be, I mean, let's not worry about it, which is just rho G with which is just M11 of LM, right? Because you will get a M21 there, but when you take the only the first n part, you will get one no LM plus M21, right? M21 will bring in something.
M2100.
That is 0 no.
Yeah.
So there is no other thing. M11 right. That's all. Right. So that's what. Yeah, that is 0, 0. Because that is 0. The mean that has mean 0, there is nothing. On the other hand, this is going to get conjugated by the M transpose, I mean, whatever. But then what you are going to get is, but you are, see, this, I mean, inside the characteristic function, you are going to have, see, you are going to have something like this, no? T rho hat of alpha is going to be exponential of something of the mean plus this, like this, no? Alpha S alpha. This S alpha will be changed to add of that using that M. But then you are going to take the only the first n entries. So you are going to put the 0, 0 everywhere else. Okay. So whatever you are going to get, everything will get killed. What I'm saying is, no, but you will get 2, 1, right?
The alpha, I mean, 0 will only be in the second space, right?
Okay. And I'm just, let me write it. So I think the new S will be the T rho. Let me write it. T rho is just the Gaussian distribution given by M11 acting on LM. Okay. This is the mean, new mean of that. And the covariance matrix is going to be M11. I think the transpose will come like this, M11. Okay. Direct sum, no direction, plus M21 transpose M21, which will be M21 transpose. No, that will be M22, no? Yeah, M21 transpose is 1, 2, right? Yeah. So this is on 1, 1, right? This is precisely. You can do the calculation. Okay. So we know how it look like. It will take any Gaussian state with mean LM and Gaussian, covariance matrix S to this. Okay. Where L is given by, L inverse is given by this. Okay. Okay. So we will do one more thing and then think about what to do next. One more theorem on the symplectic channels and then do something else.